Now we're going to look at the differentiation of the natural log function. And I know you have two burning questions in your mind right now. Wait, why are we doing logs right now? Because at the end of the last video, you told me to think about what if I have an exponential function and it's not base e? That's a good question, and I understand your concern, but you are going to want to understand the derivative of the natural log in order to help you understand the derivative of exponential functions that aren't base e. And your other question is, why are we doing natural log? Why can't we just do any log? Also a valid question. Glad you asked. But in order to be able to take the derivative of any log, just like with exponential functions where we started with base e, we need to understand how to take the derivative of the natural log, which is log base e. Moving on. Okay, what is the derivative of the natural log of x? Well, the derivative of the natural log of x is just going to be 1 over x when x is greater than 0. Why do we care about x is greater than 0? Excellent question. Think back to our logs unit, and we know that the domain of the natural log of x is greater than 0. So that has to carry through into the derivative. Now, you may be asking yourself, wait, why is it 1 over x? Why didn't we do a fun proof like we did with e of x? And that's a good question also. Really, we're not doing a proof for the sake of time. There are many different ways you can do the proof, though. I will leave that to something you can do for your own fun and enjoyment, which it would be. But for now, you're just going to have to take my word that the derivative of the natural log of x is 1 over x. You may think, well, why isn't it the same as e to the x? How e to the x, its derivative was e to the x. Remember, I did say that's the only function that has that. So natural log of x, the derivative is 1 over x. That should make sense, though, because think about what is the natural log function? Well, it's a function that is continuously increasing, but it's increasing at a decreasing rate. And so if you think about 1 over x, when x is greater than 0, well, it's constantly positive, because it represents the slope of the tangent line. Slope is always positive. But it's becoming closer and closer to 0, which is the decreasing rate part. So what happens if it is not just x? Another good question. Can we still use the chain rule? What do we do? Is there some new derivative rule? Oh my god, I have so many rules. Remember, this is getting annoying. Or should I just give up at this point? Because I know that that's a valid option. Sometimes, not always. This is not one of those cases, so don't give up. Persevere. You can do this. Derivative of natural log of u, if u is some function of x, is just 1 over u times the derivative of u, which is du dx. Or you can think of it as u prime over u. And again, the function u, where u is some function of x, has to be greater than 0. Okay, let's put this into application. F of x equals x ln of x. Let's find the derivative. What rule do we have to know? Come on. Nobody? Product rule. See? Product rule. Okay, so we're going to do the first times the derivative of the second. Derivative of natural log is just 1 over x. We just learned that. Plus the derivative of the first times the second. That's our answer. For fun, let's simplify a little bit. F prime of x equals 1 plus ln of x. All right, good times. I want you to try to find the derivative of g of x. Pause the video. Unpause when you're ready to check. All right, so hopefully you got g prime of x is 1 minus the natural log of x over x squared. How do we do that? Using our quotient rule, so bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Any questions? No? Good? Great. Moving on. Okay, here we have three different, very similar but different, not exactly the same, although I did call them all f of x, so that's confusing. I apologize for that. We're going to go with it, though. So f of x equals the natural log of the square root of the quantity x plus 1. F of x equals the square root of the natural log of x plus 1. And f of x equals the square root of the natural log of the quantity x plus 1. Notice there is a difference between these two. I want you to find the derivative of all three of these. for some of these, especially the first one, there are two different ways you could really approach this. So it's up to you what you want to do. Try those, all three of them. Pause the video, unpause when you're ready to check. Don't forget your chain rule. All right, so the first one here, f of x equals ln root x plus 1. We first want to think about this as the natural log of x plus 1 to the 1/2. So the two ways in which we can approach this is I can just leave it in this form, and then I can do my chain rule. So the derivative of the natural log of x is going to be whatever I'm taking, 1 over whatever I'm taking the derivative of. So 1 over the square root of x plus 1, and then times the derivative of whatever I'm taking the natural log of. So this is where I need my chain rule. So the derivative of x plus 1 to the 1/2 is 1/2 x plus 1 to the negative 1/2, and then times the derivative of the inside, which is just 1. Now, conveniently, this all simplifies to 1 over 2 times the quantity x plus 1, but that's one approach. The other approach is using your properties of logs. I can bring the 1/2 down in front first. So remember, we've done this, property of logs, power property, and now I can just take the derivative of the natural log of x plus 1, which is 1 over x plus 1, or the derivative of x plus 1 over x plus 1, but the derivative of x plus 1 is just 1. So we still get the same thing, 1/2 times 1 over x plus 1, which is the same as 1 over 2 times x plus 1. The big thing to note there, though, is don't forget about your properties of logs. They can help you out a lot. Next one, so this one's a little bit tricky, and I tried to emphasize this in talking, but the natural log is only being taken of x as opposed to the entire quantity x plus 1, which it is down here. So here we have to do the chain rule. So we can start out by bringing the 1/2 down, 1/2 natural log of x plus 1, all to the negative 1/2, times the derivative of the inside, the derivative of natural log of x, is just 1 over x. Now, if I simplify this a little bit, I can bring this down to the denominator, and I get f prime of x is 1 over 2x root ln of x, and then plus 1. And then the third one, here it's very similar to the second one, except for now we're taking the natural log of the quantity x plus 1. We start out the same way, though, chain rule. So 1/2 ln of x plus 1, all to the negative 1/2, times the derivative of the inside. The derivative of the natural log of x plus 1 is 1 over x plus 1. And now I rewrite that as f prime of x equals 1 over 2 times the quantity x plus 1 times root ln of x plus 1. All right, next one. This one's going to be more work. So I want you to take the derivative of y equals natural log of the quantity x squared plus 1 times the quantity x cubed plus 2 to the 6th. Pause the video, unpause when you're ready to talk about this. So this is another one where I'm going to actually show you two different ways to do this. They both get you the same result in the end. I have my answer in a almost completely factored form. It's not totally completely factored, but it allows us to compare the answers easily in this form. And so I got a common denominator, basically. That's the big thing. So we have 20x to the 4th plus 18x squared plus 4x over the quantity x squared plus 1 times the quantity x cubed plus 2. So this is our answer here. How did I get this? Well, I just went through the process of finding the derivative. So natural log, I take 1 over whatever I'm taking the natural log of, and then times the derivative of what I'm taking the natural log of. So that looks like this. Y prime equals 1 over quantity x squared plus 1 times x cubed plus 2 to the 6th power, and then times the derivative of what I'm taking the natural log of. So here I had to do the product rule and the chain rule. So product rule, I take the first thing times the derivative of the second. So doing the derivative of the second, I have to do the chain rule. So 6x cubed plus 2 to the 5th times the derivative of the inside, 3x squared, plus the derivative of the first thing. So the derivative of x squared plus 1 is 2x, and then times the second thing. So then here we looked for, okay, let's simplify a little bit. The 6 and the 3x squared become 18x squared. Here I have a 2x. Here I have an x cubed plus 2 to the 6th and an x cubed plus 2 to the 5th. So I can factor out x cubed plus 2 to the fifth and 2x. And then I'm allowed to, or then I'm able to reduce the x cubed plus 2 to the fifth with the x cubed plus 2 to the sixth in the denominator. And then I simplified a little bit, combined like terms. And then I actually ended up redistributing. And that's how I got the 20x to the fourth plus 18x squared plus 4x. So the other method would be using your properties of logs. So here I notice that I am taking the natural log of a product. So I can separate this into two separate logs separated by addition, the natural log of x squared plus 1 plus the natural log of x cubed plus 2 to the sixth. Now I can also use my power property to bring the 6 down in front to simplify this even more. Now I can take the derivative of each of these terms individually. So the derivative of natural log of x squared plus 1 is going to be 2x times x squared plus 1. The derivative of 6 ln of x cubed plus 2 is going to be 6 times 3x squared over x cubed plus 2. So the blue here is actually the derivative. What I'm doing in red, that's where I'm getting a common denominator. But notice the point of this is that the derivative process itself was much simpler by using properties of logs to split up the log first. Now I got a common denominator so that I can actually see that I'm going to get the same answer as before. So if I multiply this one by x squared plus 1 on the top and the bottom, this one by x cubed plus 2, distribute, combine like terms, and I get my 20x to the fourth plus 18x squared plus 4x over the quantity x squared plus 1 times x cubed plus 2. Next one, and last one. Go ahead and find the derivative of g of t. Use whatever technique you want. Pause the video. Unpause when you're ready to check. So this is one again where it's much easier to take the derivative if you use properties of logs first. So we can split this up into ln of t squared plus ln of e to the negative t squared. I know from my properties of logs that the natural log of e to the negative t squared is actually just negative t squared. So I haven't even taken the derivative yet, and the function looks much simpler now. Also, I can bring the 2 down in front of natural log of t squared, so I have 2 ln of t minus t squared. Take the derivative. 2 ln of t becomes 2 over t. The derivative of t squared is just 2t. So it's very easy for me to get my derivative. And in this case, also, if I wanted to get a common denominator because I needed to get this into factored form, because potentially maybe I need to find critical values. Who knows? You never know what we're going to be asked to do. But it's very easy. I can just multiply the top and the bottom of this by t as well. So, in conclusion, we need to know, memorize, love, cherish. I don't know if I'd go as far as say worship, but we want to make sure we understand the derivative of the natural log of x is 1 over x. Our restriction on the domain of natural log of x carries through that x has to be greater than 0. The derivative of natural log of u, where u is just some function with respect to x, is 1 over u du dx, or u prime over u. Don't forget that u has to be greater than 0 as well. U is some function, though. That's okay. And then also don't forget about your properties of logs. You know, I mean, I've been talking all semester, and I know you love hearing it, how everything we did first semester comes back again second semester, and it's great, Mr. Rohn, but I don't like logs. Oh, it's the worst. So yeah, you need to know those though, because it does actually make problems easier, which is what we're going for sometimes. Or another way to say easier is maybe more efficient as saving time. These are all good things to do. All right. Any questions? I've been rambling on now, and so no. Okay.